About transformations of trig functions. Make sure you guys get down the goal. You will be able to use transformation rules to graph any trigonometric function. So the same rules that we've been dealing with when we did quadratics, exponentials, logarithmic functions, they apply as well to trigonometric functions, sine, cosine, and tangent. Alright, so you don't necessarily have to get these down because remember, you've written them down already before. Just review transformations. Remember, if it's on the outside, like in these two cases, it moves either up or down. If it's positive up, negative down. And the inside, if it's a positive, it moves to the left, negative moves to the right. Remember, it's opposite whenever it's whenever it's on the inside of your function. If the negative's on the outside, you're reflecting over your x, because you're making all your y's negative. Over here, you're reflecting over your y, because you're making all your x's negative. And then, of course, vertical stretching, compression by a factor of p. Horizontal stretching, compressing by a factor of 1 over q. And please do not forget, we talked about this yesterday, that trig functions, sine and cosine, have a period of 2 pi. Tangent has a period of what? That's not what it is? Yes, it did. Tangent has a period. What's the tangent's period? Pi. Okay, so tangent's period, as it spins, is pi. And the amplitude for sine, it doesn't exist. Remember, tangent goes on and on to infinity. It has no bounds. It's not bounded in between any y value. So there is no amplitude. So tangent's period is pi. Alright? You guys remember that? Good stuff. Okay. So, your translations, we'll break it down with those translations, stretches, so on and so forth. Okay? You have sine x plus d. Okay? D representing that vertical translation because it's on the outside of the function. Remember, sine x, cosine x, tangent x, those are the original parent functions. So when you add a number on the outside, that means it's going to move either up or down. When it's on the inside, like you see here, that c is on the inside with the x, is a horizontal translation, meaning it's going to move either left and right. The same rules apply for cosine as well, and that's what it would look like. Same rules apply for tangent as well. Okay, just trade out the trig function. All right? We're going to sketch the graph of y equals sine x plus 1 and y equals sine of x minus 2/3. Now, realize that if I ever have to do an example, more likely it's going to be sine because my sine graphs look a lot better than my cosine graphs for whatever reason. So, but the same rules do apply for cosine as well. So, this first one, sine x plus 1, that plus 1 means my original sine function is going to do what? Go up 1. Okay, so let's first off take a look at we know it's bounded between 1 and negative 1. Where is it across the y-axis? At 0. And then also, where else does it cross the x-axis? Where does it cross the x-axis? 2 pi, because it has a period of 2 pi. There's one more spot in between 0 and pi. Okay? From 0, we go where? Up to 1, then down to 0, then down to negative 1 at 3 pi over 2, and then back up to 0. Okay? And it repeats that same process, just opposite. It goes down here, up. I missed that one. There it is. There's the original function. Now to graph the plus 1, the up 1, that means every point, every main point, that's 0, 0, pi over 2, 1, pi 0, so on and so forth. There.
1.
0, 1.
1.
Pi over 2, 1 is going to be where?
2.
Higher.
It's going to be up higher. This point is going to be where?
1.
At 1. This point is going to be where?
0.
At 0. And this point here is going to be? 1. At 1. So we actually take our physical sine graph and we just move it up 1 unit. You guys see that? All right. And it repeats the same process over here. I'm no longer at negative 1. I'm at 0. Here I'm at 1. Up here. So I can draw the rest of it. Now, right now, I'm not specifying what's the domain and how you should draw, but make sure that if it's an IB question, It more than likely will say what the domain is and how long they want you to graph it for, so make sure you do follow that. Now with that being said, the x-axis was your min line originally of your sine graph, or that horizontal line is now moved up as well. It's now at 1, okay? But did my amplitude change any? No, it's still 1. Did my period change any? No, okay? So moving it up or down is not going to change either my amplitude or my period. What's amplitude again? The height from the midline, and period is the length of how long it takes to repeat, the length of one cycle. All right, down here for this one. What does that negative 2/3 mean?
Are you going to the right 120
Going to the right what? 120 degrees. Well, I'm not dealing with degrees, I'm dealing with what? Radians.
Go to the right 2 pi over 3.
You're going to the right 2 pi over 3.
Can you see 2 pi over 3 on here? I don't think so.
Do you see 120?
But it's easier to look at it. You see the second one's 90, so like I'll just go in between.
Alright.
That board is awful.
It is. I don't know. Like, because we say it's what I was dealing with yesterday. Taking forever. Alright. So every point now is going to be 2/3, 2 pi thirds over 2 pi over 3. So I'm no longer at 0, 0. I'm now at what? 2 pi over 3, 0. So this point is now here. The point that was at pi over 2, 1. Where is it now going to be? Do some mental math. What's pi over 2 plus 2 pi over 3?
210.
7 pi over 6.
Going to be
7 pi over 6.
7 pi over 6. Common denominator?
Get good.
Common denominator? 5 pi over 3.
Move 1 over.
Okay? Then pi plus 2 pi over 3. Common denominator would be 3. So 5 pi over 3 would be the next one. Is everybody following along here? All we're doing is we're just adding 2 pi over 3 to all of our original x values. That's how we're going to get, that's how we're getting these red numbers. Okay? The next one is 3 pi over 2 plus 2 pi over 3. What's that going to be? 2 pi, it is 13 pi over 6. And the last one was 2 pi plus 2 pi over 3. What is that?
8 pi over 3.
And there's your curve. Moved over 2 pi over 3 radians. Yes.
Do you want us, if we're doing that problem, do you want us to show all that at the bottom where you have all those lines?
If the graph is not labeled with these values, then yes, you want to make sure you write them in to represent that it's being moved to the left and to the right, that many units.
So you can't just put it there.
Make sure you label. The other side, with
Shoot me.
it'll follow pretty much the same pattern. If you look, it's pretty much over here.
So we don't have to write in those values. Okay, thank goodness.
It is 8 pi over 3.
I just didn't go for it.
Did it stop spinning or just Alright, there you go. Questions on transformations?
Is there any way to do the radians like in a We have to like,
I mean, you could convert them to back to degrees and then convert them back to radian, but that probably take
It's just as long.
just as long, just to get the common denominator. Alright, questions on this? Stretches. So we'll start with vertical stretches. Those are in the form y equals a sine x, or y equals a cosine x, or y equals a tangent x. Okay? So it's a number that's in front, just like before when you had your vertical stretches, it was a number being multiplied to the original function. If a is greater than 1, we're talking about the absolute value of a. It stretches away from the x-axis. Okay? Stretches away, so that means it's getting basically skinnier, vertically stretched. If a is in between 0 and 1, the absolute value, it compresses closer to the x-axis, so it's basically getting squished vertically. If a is negative, though, that means it is reflected over the x-axis. After it's flipped over the x-axis, then it's going to continue to either stretch away from the x-axis or even closer to the x-axis. All the y values get multiplied by a of your original sine, cosine, or tangent function. And lastly, a also changes the amplitude of your function from 1 to whatever the absolute value of a is. Okay? So if a is 3, my amplitude is no longer 1, it is now 3. If it's negative 2, my amplitude is no longer 1, it is now 2. Still positive, it's the absolute value. Okay? So what we're going to do is probably graph just one so I can get to horizontal stretches. To make sure that you guys will be able to do your homework. Okay? So we're going to do this very first one. It's going to be cosine of 0.25, or 0.25 cosine x. So this right here tells us that it's going to be a vertical stretch by a factor of what? By a factor of 1/4, 0.25. So no, none of my x's change. It's just my y's. Okay? So I have positive 1, negative 1. I'm just graphing the original cosine function here. Just as a reference so you can see the difference. So this point that's at 0, 1, all your y's get multiplied by 1/4. So what's 1 times 1/4? 1/4. So this point is now here. What about this point? It stays the same because the y coordinate there is 0. So 0 times 1/4 is 0. What about here at pi negative 1? It's going to be a negative 1/4. What about here at 3 pi over 2, 0? Same. And over here at 2 pi 1, it's going to be at 1/4. And for the other side. And isn't it compressed? Not vertically stretched, but compressed. A is in between 0 and 1, is closer to the x-axis. Do you guys see the difference? Good stuff. Actually, we do have some time. That didn't take us too long. Let's do this one. What does the negative 2 mean? So it is reflected over the x-axis and then stretched vertically by 2.
wait, how come the one above was a, never mind.
Things like in this case, you have to flip it and stretch it. You can do it all in one. You can do it all in one. Okay? Just real quick, I'm just going to do the original cosine curve so we have that as a reference. So am I going to stretch it first and then flip it, or am I going to flip it first and stretch it?
You can both at the same time.
You could do, well, that's the thing, but am I gonna stretch then flip, or flip then stretch? Flip then stretch, okay, so this point, that was at 0, 1. If I flip it, it goes to 0, -1, and now I'm gonna stretch it, so it's gonna be at 0, -2. My y's get multiplied by 2. What about this one? 0. Say 0, and when I multiply by 2, it's 0. Goes to +1, and then when I stretch it, it goes to 2. This one here at 3 power 2, 0 stays. But this one, where's it going to be at now? At -2, because I flip it and then stretch it. Similar pattern over here. Flip it, stretch it. Stays the same. Flip it, stretch it.
Why wouldn't it be?
Because we're multiplying, we're not adding. So basically we're just multiplying all of our y's. Questions? So remember, vertical stretches change your amplitude. Horizontal stretches are going to change your close to the y-axis, or we're getting further away from the y-axis. So horizontal stretches, this time the variable is b, and so the inside with the x being multiplied. If b is greater than 1, the absolute value of b is the opposite as it was for the vertical stretches. It gets compressed to the y-axis, so that means it's getting shorter. Our period is getting shorter, it's getting closer to the y-axis. However, if the absolute value of b is in between 0 and 1, so in other words a fraction, it's getting longer, it's stretching away from the y-axis. And then if b is negative, it's reflected over the y-axis, okay? So you can think of it as this: every x is multiplied by 1 over b. Just like before when we were doing horizontal stretches with just regular quadratic functions. It was 1 over b, or 1 over whatever that number was. 2 pi over the absolute value of b. So b was 2. Then our period will go from 2 pi to pi. And then tangent's period will change from being just regular pi to pi over the absolute value of b. I'm going to try to squeeze in one example of tangent so you can see how that works. With these stretches horizontally. So looking at this one, we have tangent of 2x. So that means our period is going to be not pi, but pi over the absolute value of 2, which is just 2. So no longer am I going to have asymptotes at -pi over 2 and pi over 2. It's going to be halfway in between that. -pi over 4 and positive pi over 4. Because it's getting shorter, it's getting smaller. Alright, I'm multiplying all of my x values by 1 over b. That's where we got pi over 4 from. Okay? Alright, so that point that was at pi over 4, 1, gets multiplied by 1/2. So it's going to be at pi over 8, which is halfway in between. So tangent basically gets skinnier, it gets closer to the x-axis. And then you can repeat that for all the other ones after that. Okay? For cosine and sine. Alright?
Push it.
It's getting closer to the x-axis because this number is bigger than 1. If this was a 1/2, it would have gotten like wider. Okay? So your homework, guys, I won't